We have a system of three equations with three unknowns, which is a quadratic system, so we could potentially use either Kramer's rule or the inverse matrix method, because we can find determinants here. But we will use Gauss-Jordan method here, the classical Gauss-Jordan method. We begin with creating an augmented matrix, which means we write the coefficients at the unknowns, x's, y's, and z's, then a vertical line which plays the part of equal signs, and the right hand side of the system. The goal here is to have a identity matrix, or at least a matrix in the row reduced echelon form. As many pivot columns, as many pivots as possible. We use the classical method, so we're going to move along the diagonal, starting with the top left entry, this one right there. We want to eliminate every other entry in that pivot column below that pivot, which means in the second row we have to remove the 1 by subtracting our 1, and in the third row remove the 2 by subtracting 2 r1. That way the first row, of course, will not be changed. The second row will be changed when we subtract r1 from it. So that to -5, -3 -0, and -5 -1. And the third row, of course, similarly subtract twice r1. So here we go, 4 - 2 is 2. Okay, we're moving on, classical method, so our next entry on the diagonal is going to be our next pivot, the -3. First we're going to change it into a 1, simply dividing by -3. So the first and third row will not be changed, the second just divide. And now our pivot is a 1. We want to eliminate everything else in that column below that pivot, which is the -6. By adding 6 times r2 to it, we shall get a 0. First row unchanged, second row unchanged, and the third one we're gonna have a 0, 0, 1 plus 6 is a 7, and 2 plus 12 is 14. Okay, next entry on the diagonal, 7 is our next pivot, so first make it a 1, divide by 7, like so. And now that ends the first step of the Gaussian classical Gauss-Jordan elimination. And now we're gonna go backwards. So start with the bottom right entry right here, and eliminate everything else in that column, everything above it. So here we have just the second row. In the first you have a 0, in the second you have a 1. So the operation is from second row subtract third, and you shall get a 0 where you need it. Okay, and then almost finished. Next pivot on the diagonal is going to be right in the middle, and the only entry to eliminate above it is the 5. So from the first row subtract 5 times row 2, and that 5 will become a 0. First row changes just a bit, and the last two don't change at all. Okay, we have 3 pivots, 3 pivot columns. We have identity matrix 3 by 3 system, so 3 unknowns, which means we have exactly one solution. Oh, there seems to be a mistake here. Hold on. It shouldn't be a -4, it should be a 1. So 0 here and a 1 over here. Okay, so we have exactly one solution. And just as we changed in the first step, the system of equations was changed into augmented matrix, now the augmented matrix can be changed back into a system of equations. So from the first row you have 1 times x plus 0 times y plus 0 times z equals 1. In the second row you have 0x, 1y, 0z equals 0. And in the third row you have 0x, 0y, 1z equals 2. And this is your solution.